Hello everyone and welcome to this crash course on large language models. So we'll start by, we're going to talk about the architecture, the training, and the practical implication of LLMs. So LLMs are basically your ChatGPT, Gemini, Claude, Llama, and they are basically neural networks, AI systems that are neural networks that are trained on massive amount of data of text to basically understand and generate uh, language like humans would in terms of generating language. The model is probabilistic because it's based on a statistical model. Neural networks are statistical in their nature, which basically means it's going to remember what it has seen frequently, the frequent and the very strong signals, and it's not going to remember things that are not so much frequent in the data. So we always have to keep that in mind. So when you're engaging with ChatGPT, you have to always remember that it will not remember everything that it was trained on, but would remember things that it's seen very frequently in the training. Now remember, LLMs, because they're based on neural networks, they reflect pattern in their training data, which might include biases, incorrect info, and sometimes fabricated information, because at the end of the day, they're trained on data coming from the internet. And if then that data is full of incorrect information and also missing information, we're going to see that too. The architecture is we use neural networks. The LLM architecture are basically neural networks. And LM and neural networks, again, are basically these very humongous network that are basically mathematical in nature, statistical in nature. LLM, they use multi-layer neural networks. So probably if you've used neural networks for things like forecasting or some other form of application, you're probably used to a neural network with 2, 3 hidden layers. But no, for LLMs, they're using many hidden layers, almost 90 to 100 hidden layers. So we're talking about humongous neural networks. And these layers include embedding layers, memory layers, and others that we're going to discuss in this crash course. So how much does the LLM learn? I mean, it learns about what a human would probably take about 2,600 years to learn, to read. So if you were to take an average human, it would take them 2,600 years, 2,600 years to read what ChatGPT has read. And that's given that this person probably is awake 24 hours, 7 days a week. So, I mean, we're talking a lot of information. LLMs digest basically the whole public internet. So all the books that have been digitized by Google and put on the internet for the last 20 years, it's read all that, all the Wikipedia pages and much more. So a lot of human texts. So almost we could actually say that it's almost read all human knowledge. Um, Human knowledge that is available in the internet to public. So using neural networks, so we're looking at a gigantic. So if you've done some statistics, you have some statistical background, and nowadays I think even in high school, kids are doing statistics. So think of a neural network as this gigantic linear regression model, except it's not linear, it's nonlinear, and it has nested functions within it. So you're looking at an equation that is humongous, really big, lots of mathematics, lots of equations. It would probably, if I were to actually write down the parameters of the neural networks, it would take me 500 years to do so, to just write it. So you were talking about gigantic neural network. So we need two things in LLMs, and LLMs require two things: high quality data and lots of it, and a lot of compute, lots of computers to run these models. In LLM lingo language, we call We use the word GPUs, which are much more efficient than CPUs. They're really geared towards the matrix multiplication part of the LLM training, because LLM training neural networks, they require a lot of matrix multiplication, and GPUs are really good at that. Now, if you're into gaming, then you probably know what GPUs are. They're geared toward more geared toward people who gamers, because they use a lot of GPUs, and gaming requires some of them same requirement as LLMs. So we're gonna start talking about tokenization, then we're gonna talk about pre-training, then post-training, inference, and finally we talk about prompt engineering. So let's start with the idea of tokenization. Now, the LLMs don't see words. When you read the text as a human, you see words, but that's not how LLM do it. They see vectors. So each word represent a vector, a long vector, and itself, the word is not actually a word, it's actually a token, which is again is a number. And that number represent a vector that is again very big in size. So LLM operates on tokens, not characters or words. The model works through tokens, which are effectively numbers and probabilities, and not true understanding of how letters make up words. So LLMs don't understand how letters make up a word. They see a word as a number, and so on. This is the main reason why LLMs are really bad at spelling or counting number of letters in a word. So the famous example is the word strawberry. You ask LLM how many R's are there in strawberry, and it struggles. Now, of course, with the newest models, it's no longer struggling. Maybe it has been hard-coded nowadays or not, or something else. But at the end of the day, they do struggle with spelling and counting of letters, because they don't see letters like we see when we read text. So now let's take this example, and this example is going to be, there's a link here to an OpenAI tokenizer that is going to help you see words like LLM sees them. So the link takes you to an OpenAI platform tokenizer, and if you take the first word that they're asking us to tokenize, which is wood, we get a 1 token, 4 characters, and if we pressed on token ID here, we get this number 8172. So 1 token, so wood is 1 token, and it has an ID which is 8172. And again, LLM is going to see that ID 8172. It's not going to see the word wood with WOOD. Brainstorm, it's going to see it now as 2 tokens. So we could actually go and check and see. So if we write brainstorm, we see 2 tokens, and so it sees as brain and storm as 2 separate tokens, and the token ID is the following. And we could do the same for all the other examples. Now remember, in the link in the description, there's this PowerPoint. You could find the PowerPoints, and you could actually go to the OpenAI tokenizer and find out how words are represented in terms of tokens. So we said we're gonna start with tokenization, then we're gonna talk about the two most important things about LLM trainings, which is the pre-trained and the post-training. The pre-training and the post-training. So training of LLMs consists of two items. There is the pre-training and the post-training. The pre-training is going to feel like an autocorrect, where we're trying to, I don't like the word guess, but predict the next word. So the model is trying to predict the next word. In post-training, it's no longer an autocorrect. It feels like the chat bot that you're used to when you go engage with ChatGPT. So it can do questions, answer queries. So the steps in training. So let's start with the pre-training. So in the pre-training, we're gonna talk about there is tokenization. So always it's gonna start with tokenization. Then it's gonna start with word embedding, which basically embed a vector for each token. Again, we're not using words. LLMs don't see words; they see tokens, and each token has an embedding, a vector, a very large, humongous size vector with many numbers. Then we're going to talk a little bit about transformers. We're going to talk about pre-training. When do we conclude pre-training? What do we do after pre-training? We do something called fine-tuning, where it's also called post-training. Now, after the post-training, the weights are going to be finalized, and the network is going to be ready for inferentials. And inferentials, what do we mean by inferentials? Is basically when the user prompts LLM, ChatGPT, and so on. In inferential, the weights are no longer updated, and maybe it won't make too much sense right now, but in the coming slide, it will make sense what I mean by the weights being updated. So here, so pre-training is basically the most computationally expensive. It involves training on massive datasets, use large clusters of GPUs over weeks or months. So this is where we said that the LLM is gonna read the whole internet, the public part of the internet. And the idea is to learn general language patterns and representations. Then we get to post-training, which requires less compute. The model is already trained, but we need to further adjust so we need to further adjust it on smaller task specific with human labelers. And this is quite important for it to take the persona of a chat agent. Now, inference is the least compute, and this happens when you engage with ChatGPT and ask questions. And here we're running the trained model to generate prediction or responses. But remember, maybe inference is small compute, but remember, there's millions of users using ChatGPT every day, and they're using it not once, probably many times a day. So we end up with probably hundreds of millions of prompts. So what seems to be very low compute ends up being a lot of compute. So let's talk about so pre-training. The basic idea is to, and it's also called a base model. A pre-trained model has another name. It's called the base model. And we are trying to predict the next word in a sequence. And the training process is going to be a feed-forward neural network, and we're trying to predict the next word. And actually, it's not. We're going to see a probability distribution of that word, of the different words for that. So the cat sat on. The next word, there is going to be a probability distribution. Probably the more would be the more accurate, will have a higher probability distribution, but there could be many other items that could be part of that distribution. Now the model moves on to compare that predicted word with the actual word, and with backpropagation. And backpropagation is going to adjust the weights of the neural network. The neural network is going to start with some random weights, but as training happens, these weights are going to be adjusted until the time we get the neural network to correctly predict the next token or the next word. So it's autoregressive. It's one word at a time, and that time, so we start with one word prediction, and then prediction is added back to the input, and so on. And we're going to see that in some figures. So this is a good illustration. So we have the cat sat on is the input. You have the model, and then the output is going to be mat and this is a simplification. Of course, the probability distribution is going to have more than four words. It's probably going to have dozens to almost hundreds. But here we see the highest probability distribution is 0.21. So we pick the cat sat on the. And then we feed the back into the input. So the cat sat on the. And then the mat gives us the highest probability distribution, and we pick mat. Now here, this is also this is a simplification. You are gonna have more words than just 5 words. You're probably gonna see a word floor, because the cat sat on the mat. It could be also sat on the floor. Now, of course, we don't LLMs don't always pick the highest probability among the words. Sometimes it pick a less probability depending on the entropy that we set the model on. And this is something we're going to talk about when we go into prompt engineering. So pre-training is a form of self-supervised learning. So it is supervised because the model has a target and an input. So it's trying to predict the next word, and the next word there's a target to it. So it sees the target and it compares to that target. But it is self in the sense that it on its own, it's gonna be masking the input and the output and changing that all the time to get more instances. So the first thing that the people that made ChatGPT, probably the first task they had to go through is data collection and collecting all that data from the web. And then they had to tokenize these words into actual tokens. And then the training had to happen. And this is autoregressive training. So the input is all but the last token, and the target is the last token. So take any sentence, the cat sat on the, that would be the input, and the target would be the floor, for example. And then we go, the cat sat on the floor, that would be the input, and the target would be maybe comma or something else, and then comma is chosen, and so on. So it is autoregressive in nature. So this is a schematic of it. So we have the input sequence with many tokens, and it's going into our computer model, our neural network, which is basically, we're talking about billions of tiny connections of weights and biases. And this is why I mentioned it would take you 500 years to write the weights. We're talking about some humongous neural network. We're not talking about a small neural network here. And then the output is going to be a probability. It's not going to be one token. It's going to be a probability of tokens. So this is another illustration. So we have the sample data. So we're running things in parallel, like LLMs. They're running. So the chicken cross da. So that would go into the input where there's tokenizer and there's some form of self-attention and word embedding, and we're going to talk about all that. And then what we have here is the chicken cross the road is the prediction. And remember, here it's not just road, there's other words, but you end up choosing road because it has the highest probability, and so on for the other words. The dog ate his food, right? So it's very important to remember that LLMs do not produce next token prediction, but a probability distribution of tokens. So we have to understand that. So LLMs, we could play with this distribution, as we will see in prompt engineering. and the dog ate his food. It doesn't have to be always food. It could be something else. Maybe for creativity reasons, we might want to use another word to make things more creative. So the weather today is sunny. Yes, that's the highest probability given, but maybe we want it to be cloudy and so on. So there's also entropy that is going to play into this distribution. So let's do an activity here, and again, you please pause the video so you could read the. So imagine for a moment that the input to an LLM neural network consists of words rather than tokens. So let's just assume it's words, not tokens. Suppose the input to the pre-trained model is the cat sat on. The actual text is the cat sat on the floor and slept. So the LLM is gonna see the 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 whole sentence, the cat sat on the floor and slept. But we're gonna feed into the input just the cat sat on. Now envision the training process and the autoregressive prediction of the next word. So let's go step by step of what actually happens. So LLM is going to label the cat sat on as input and the as target. And this is what we're talking about when we say self supervised. This is the self part of supervised, is the ability to do this, to label an input and label a target. Then the neural network predicts the next word. Let's say it predicts dog. So it says the cat sat on dog. Now the neural network would take that prediction and see that there's an error here. The prediction is dog and the actual is da. So there's a difference. And now what the neural network is going to do is they're going to do something called back propagation, where the neural network is going to adjust the weights in a way, and the gradient search gradient descent is going to make sure that our next prediction is closer to the truth. So we're moving in the right direction. This is the whole point. So we know dog is not correct, but we want to move towards that. So we adjust the weights, and after many runs, we will actually arrive at the correct prediction. And at that time, we stop and we say, the cat sat on the is the correct, the is correct, and dog is not correct. And then we feed it back as an import, and we as an input, and we start we want to predict the next word now, which happens to be the floor, and so on. This is what happens in the actual training. So let's give you a chance to read the next activity now. So again, if you wanna, you must download the PowerPoint for this presentation for you to be able to use these links and go, and the learning process would be much better if you download the PowerPoint and click on the links and so on. So the question here is, suppose that the input of the pre-trained model is the cat sat on. This is the input. Using the GP2 base model from Hugging Face within a Google Colab environment, run the Python code provided in the Colab notebook below. So we're gonna just go on to this link to generate a prediction for the next word and display the resulting word sequence. So the idea is we wanna see what the model is actually going to give us. This is a real model, the GPT-2 base model. So it's real. This is what an LLM is going to feel like. And this is a base model. It hasn't been post-trained yet. So let's see how it's going to deal with this, the cat sat on. So we see here the prompt. So this is, we're using GPT base model, and the prompt is the cat sat on the, and we run it. I'm not gonna run it here because sometimes it takes a while to run, and not too much of a while. It shouldn't be taking you 5 minutes, but you could try it on your own and try to run it. It should be maybe a minute. Sometimes it depends, and depends on the server. So here we see that floor is the highest probability. So that's what model would probably pick, floor. We see here bed, there's couch, there's ground, there's so many choices. Now, because of the training model, it just happens that floor is the most frequent follow-up when the model is presented with the cat sat on the. Now, the nice thing about this is you could try other words, other sentences. So you could try the dog ate his, or the cat ran with. You could try different sentences and see what the output would be. So going back to the Python code, we have the five next tokens, and it's going to predict floor as the highest probability distribution. So the predicted next word should be floor. Now, again, when we talk about prompt engineering, we'll show you that sometimes it doesn't pick floor, but it will pick something else depending on the temperature you set. We're going to talk about that later on, but for now, it's going to pick the highest probability, which happens to be floor. So now we discuss the architecture, the actual architecture of the neural network layers in LLMs. So what happens is we need to embed these words, and the words we have to embed them in a mathematical manner. So each word, for example, like king and queen, is actually fed through a vector of numbers. Now, of course, the number is not four numbers, it's probably thousands of numbers. And so a word like king and queen will have different embedding in terms of number. But the thing is, and the proof that these neural networks actually understand the semantic of these words, so they have the meaning is not just words, is the fact that if you take the word of king, the vector of king, subtract from it the vector of man, and you add on top of it woman, you end up with a vector that looks like queen. And this is quite important for us to understand that these LLMs, they actually understand meaning. So they do understand the relationship between words. They understand how king is uh, compared to queen in terms of meaning. So that's very important. So let's do an exercise on this. So again, for each activity, you can download the PowerPoint in the description. And more importantly, please pause each activity so you could have the time to read it well. So let's imagine that we train a model that learns the following simplified word embeddings. So these are simplified, only two dimension, like an X and a Y. What does this embedding say about LLM understanding of semantics, meaning of words? So what we want to do is we want to take king and subtract it from man and see if it's equal to queen. And if we do that, we take the king, which is 8, 6, and you subtract from it man, which is 6, 2, and plus the vector of 5, 1, which is corresponding to woman, we end up with a vector of 7, 5, which is exactly queen. This is just an illustration. Of course, in real LLM vector representation, we're not going to get an exact number, but it's going to be close. Okay, and this shows that word embedding captures semantic relationship, meaning of words. So remember, I'm just simplifying things with two numbers. Actually, the actual vectors that represent these word embeddings they have hundreds or even thousands of dimensions. And now we move on to transformers and self-attention. Some might argue that chatbots are merely repeating what they've seen during the training. And but the truth of the matter is, through self-attention or probabilistic modeling, they generate new texts that reflect patterns in the relationship learned during the training. So it's not just memorizing. We were understanding deeper patterns about these words, not simply just memorizing. And these LLMs, they understand semantic. But how is this so? How is this so? How does these LLMs understand the meaning of things? And it seems to be, some, like I said, some people argue that it's just an autocorrect. Now, if it's an autocorrect, how does it understand the difference that king and queen are somewhat similar and so on? And the main reason is for something called transformers, which is self-attention. So in transformers, self-attention is basically in before transformers, and if we talk about neural networks, recurrent neural networks, what a model used to remember is mostly the recent data. So if you take textual data, then obviously any word is going to be highly related with the word just before it, and a little bit less and less and less as we go backward in the sentence or the paragraph. So self-attention is something that is revolutionary because it allowed words to talk to each other and allowed words to not only be concerned about position but also context. And so even if a word is really far away from where from the token we're trying to predict, it might have more influence than another word that is closer to where the prediction is happening. So we're trying to find relationship between words. And again, with RNN, as I mentioned, recurrent neural networks, older data usually that is far behind is not so much, it would not influence the prediction. But with self-attention is a completely different story. If these words actually are important to the context, so regardless of how far they are back, they still have a relationship and an influence on our prediction. So here's another activity, and I'll give you, please pause the video and read it, and we'll do it together. So transformer architecture introduces attention, the ability of the model to focus on relevant tokens regardless of their distance in the sequence. So the meaning of the phrase depends more on the relative importance or weight of words than their exact order. So with transformers, predicting the next word, the cat sat on the. So here I'm basically in this activity trying to ask you, imagine that we're using the cat on the as an output. Which of the words would matter more? And now I'm talking to you as the speaker, the speaker of language, the human that actually speaks the language, knows what's important in the sentence. And if you actually think about it, that you would pay more attention to cat and on in this sentence because that's what's going to decide the next word. That is an article and it's associated with, I mean, it could be anything. It doesn't give us a lot of information, but on gives us, and the cat is giving us the most information here. And that's exactly what transformers do. They pay most attention to on and cat because they carry the strongest clues about what's likely to follow, such as mat or floor. So now we're ready to talk a little bit about the architecture. So we have the input data, we have the tokenization, and after that, this is where the neural network starts. So the input data is just words, phrases, and then they convert it to tokens, and then you have an embedding layer in the neural network, which is basically going to convert these words into vectors. And then we have the transformer blocks where you have self-attention, and this is the transformers, and then the normal feed-forward network. If you've done a class on, or if you read about neural networks, then you know what a feed-forward network is. Basically just a neural network. And then there's an output layer and so on, and then there's the training and loss optimization, the gradient, descent, and pack propagation. So what is quite unique is the self-attention for LLMs. They excelled because of self-attention. The ability for words to no longer just, it's a case of order, but it's also in the case of importance and weight. in the case of context. It brings more context into the actual prediction of the next word or next token. So now, so far we talked about the pre-trained model, which is what we call the base model. And for example, for ChatGPT, most of the training model, the good quality the training model is coming from the public internet that is verifiable, such as Wikipedia. So, for example, Wikipedia is considered to be high quality data for ChatGPT. Pre-training teaches the model to predict the next word, not to reason or follow instructions. So it's basically trying to predict the next word. It's not there to have a discussion with you. It's not there to sort of help you. And so it's basically just trying to predict the next word. It doesn't truly understand what's being asked. Now, these training models, and so for example, a base model will be really good at predicting. So for example, if we take some text from Wikipedia and give it to the base model for ChatGPT, it would almost certainly predict the text because that's considered high quality data. But if we start to ask it more about the text, things about the text, that is not part of the text, then it would not be able to do anything like that because it's just a token predictor at the end of the day. So this is why fine-tuning is needed. This is why we need a post-training. And the post-training is what we're trying to do is turn the base model into a helpful AI assistant. So when you use ChatGPT, you don't feel it's predicting the next word, you feel it's answering a question. There's a chat going on. And this is done by feeding the model questions formulated by humans with ideal human answers. And the idea here is they're gonna prompt, they'll basically write code where they ask a question with the human as the subject, and then they would give an answer, and they would have labeled that as AI. So in this post-training, the weights of the neural networks get updated. So when you finish pre-training, the weights have been updated during the back propagation and so on. Now in post-training, we take that pre-trained model and we update these weights further. Now remember, we don't want to do extensive post-training because that would mean some of these pre-trained weights are going to also change, and that would be catastrophic because, this is the most expensive part of the training, so we don't want it to forget the stuff we trained it on. So post-training has to be very strategic and it has to be done in a very smart way. So the idea here is you have a human asking, what is the capital of France? And then it would present an answer with AI labeled as AI, the capital of France is Paris, and so on, and so many questions. And what you're trying to do is give the machine, the LLM, the opportunity to understand what a chat is, what it means to go back and forth with question and answers. And this is actually part of post-training. Post-training is not all that, but that part of post-training is called supervised fine-tuning, SFT. So let's have you please pause the video and read activity 6, and we'll go over. So imagine you trained a language model only to predict the next word in text, and that's exactly what a base or pre-trained model does. Now you ask it, can you help me plan my study schedule for finals? What kind of answers you think would the model give, and why it might fail to give a truly helpful response? Now, actually, if you actually go ahead and use the base model I've shown in previous activities with the GPT-2, I believe, Then what it will give you, so it will basically try to continue the phrase. So I am not sure if I can do it. I'm still trying to plan my schedule. So it would say the input would be, can you help me plan my study schedule for finals? And then it would say, I am not sure if I can do it. I'm still trying to plan my schedule. Now, this didn't follow your instructions, it didn't adapt to your need. It's just trying to find what is the most probable word in the sequence without really answering the question. And that's what a base model is. So post-training, we mentioned there is fine-tuning, which is SFT, supervised fine-tuning, but there is another part of the training, the post-training, which is reinforcement learning. And SFT is very simple. It's question and answers that a human labeler, he basically or she writes it down. But reinforcement learning is a little bit different. Here you're giving a set of questions and you allow the LLM to give an answer, and then you reward the most preferable response with the highest ranking. So if you get a good response, then you give it 9 out of 10. If you get a bad response, you give it 5 out of 10. And this resembles more how humans learn. So humans don't learn by guessing the next word, and they definitely don't learn by having the answers. So a student is not given the answers to an exam, as in the case of SFT, but it's rewarded with partial marks or full marks depending on the performance. Here we are pushing AI to improve and develop strategies. So the idea here is we want to push it so it can improve strategies. So reinforcement learning is going to help it develop strategies. SFT is just is answer and question, and we're trying to have it mimic this behavior. So reinforced learning RLHF produces better judgment, alignment, and strategy for producing useful answers. So here we see this example. So if our neural model actually predicted what a cat is correctly or identified a cat, then in an SFT, you just give it a pass. While in RLHF, you give it an actual score, 8.2. So maybe it gave you a cat, but it's not a very clear. So for example, image generation, it generated an image for a cat, but it's not very cat-like. So you might give it a 5 out of 10. It gives you something that looks much more like a cat, then you give it 8. It looks much more like a cat, then you give it 9, and so on. So here's the next activity. Again, please pause the video and read the activity. So imagine an LLM has just been supervised, fine-tuned to answer questions. You notice that sometimes it gives answers. So after it's been trained, you notice that it gives answers that are technically correct, but they're a bit vague or slightly misleading or not phrased in a helpful way. So how could you teach the model to prefer better answers without changing all of its pre-training? So we use reinforcement learning from human feedback, and we know what the answer is. So we give it the question, but we don't show the answer. We let it try out and then reward it for how close it is to the answer. That's the strategy. So the model learns a strategy for producing responses that humans consider better. It's not just memorizing, it's learning how to make better choices given the context. Now we move on to start talking about the post-training effects. So post-training, as we mentioned, we have human labelers, and the people that are doing the labeling for these in post-training, they're not going to give an I don't know answer. They're going to give precise questions that have precise answers. So what's going to happen is the model learns that providing a confident answer, even when uncertain, gets higher reward. And this is a problem. So the idea here is the LLM wants to seem confident even when it should say I don't know. So the models, they learn to imitate human responses because the labelers provide confident, direct answers. So they start producing plausible sounding but incorrect information. Now, what is the solution to that is the human labelers should include questions where the correct answer is genuinely I don't know. So the idea here is to have questions where the answer is I don't know. Maybe there's some questions where humanity or science hasn't really given an answer to. So it would provide the computer or the AI with an answer I don't know. And it's telling the LLM that it is okay to say I don't know. So the LLM learns that this response is acceptable. Now, hallucination. So what we've just seen here, the fact that the LLM doesn't know the answer but fakes an answer is a form of hallucination. So here the idea is incorrect, nonsensical, or not grounded responses. And this is rooted not just in post-training, it's also in pre-training. So the output sounds plausible and grammatically correct, but is inaccurate. The model invents details, sources, or facts that do not exist. In the early days of ChatGPT, I used to ask to provide references for certain questions, and the references that ChatGPT used to provide was all made up. It's not true. You look at the reference, you try to look for it on the internet, it's made up. I think that has really improved in the last few years. Now, what is the source of the problem? Where is the problem coming from? Well, first of all, we said in post-training, because humans don't give the I don't know option to machine when they're prompting questions and answers. Also, there's bias in the training data. Remember, these LLMs have been trained on the public internet, and there's a lot of false information on the internet. That's the reality. There's errors, there's fiction, there's contradictions. Also, there's the idea that there's also fiction. There's stories that are fictions. I mean, is LLM able to recognize the difference between fiction and non-fiction? All these are going to come to at play. They'll come to play. So even when having the whole internet, public internet as training data, there's still many niche and missing gaps in the human knowledge. Statistical nature of LLMs. LLMs vaguely remember the training data. It does not know it by heart. And also there's the fourth thing, the source of this problem is that LLM doesn't remember everything it read. Doesn't remember the 27,000 years of human worth of reading. It doesn't remember it all. So what it doesn't remember, it might want to fake an answer for. So I mean, there's many sources of that cause hallucinations. So we could address each one of these problems. We could address it by having post-training where the answer I don't know is available, having a model that is that relies more on high quality data rather than low quality data. And the ability for the model overall also to understand, and from the user side, it's very, very important for the user to understand that these LLM models are statistical, stochastic, which basically means there's always room for error. You know, we have to understand that this is the most important thing to take from this crash course, that LLMs actually make mistakes. So let's spend some time on this activity. I'll give you, so please pause the video and think about this activity. So can you think of potential solutions for hallucinations? So what we've just went through, what do you think are good solutions for hallucinations? So allowing the LLM to say, I don't know, part of the training, especially post-training, for an LLM to know that the option of saying, I don't know is there. There's certain questions, certain type of questions that the proper answer is, I don't know. Built-in citation API for grounding answer in source documents. So we could actually help during the training process of actually or not only in the pre-training, also in inference, allowing these machine learning models to use the internet to check the validity of certain information. And on the inferential side, because remember, uh, this is not just on the side of the company that trains these LLMs. This could be on the user side. So, for example, when we want the LLM to actually say I don't know when it does not know, we could do that in inferential. When you're as a user using ChatGPT, maybe you could write something like, please, if you don't know the answer, say I don't know. You could write that in the answer. Be neutral, for example. You could say be neutral. Be fair. Acknowledge if you don't know this question. So anything in the prompt that you could write to make sure that the LLM has that option, is prompted to actually do that. Because remember, it's trained to be helpful to you. And if you tell it that, please say I don't know when you don't know, then it's gonna listen. References, you could also ask it to provide references. After it gives you an answer, ask it to provide references. This is something you can do. You can actually also LLMs. In LLMs they connect to external knowledge sources, something called retrieval augmented generation (RAG), which is basically a way to verify information. So a way for the LLMs to go and see what is factual and what is not. But you, on the side of the user, you could actually provide documents to ground the LLMs. So, for example, if you're asking it a medical question, maybe you have a document, a PDF that has to do with this medical question, then try to upload that document to ChatGPT. That would help immensely for LLM to actually realize that to verify its own information and to make sure that the information that comes out of the LLM is actually factual. So after the model is finished with pre-training and post-training, we're ready for inference. And inference is basically the idea that when the user actually uses the AI chatbot. So the user is actually using ChatGPT, is actually using Gemini, is actually using the LLM. So the model is no longer being trained. We're using its final updated weights to make actual predictions. So in training, we learn the next token, and during the training, the weights are being updated. In inference, we use the already trained finalized weight, and we basically start asking the chatbot questions, and the chatbot should be able to answer us. So again, what's happening here is your prompts are basically being an input to a forward neural network. So it's gonna predict things 1 token at a time, and it's going to sample from probability distribution, and it's going to append to the context and repeat until it finishes, completes the response. And we're going to see that in the next slide. So context window becomes very important, which is basically the working memory of our LLM. And we're going to define it in later slides what it means. But for us, for now, let's think of it as the working memory. It is the most reliable source for recent tasks. Um, so remember, the things that the LLM learned is not remembered 100% because it's, as we said, it's statistical. And that's what we call parameterized knowledge. Parameterized knowledge is vague recollection, remembering training data pattern, less reliable. So it's less reliable than the context window, which is information given to the LLM right now. So let's see how inference works. So if somebody prompts the LLM or ChatGPT, what is the capital of France? Now, the ChatGPT is going to go through the forward pass and it's going to produce the as the next token. Then it's going to be basically taking the and it's going to join it to the input. And then we predict the next word, which happens to be capital, and that's going to be joined with the input again. And then we predict of, and after that, France is, and finally we get to the point of Paris. So there's auto regression happening when we do inference, just like we seen in pre-training. But the only difference here in inference, it's only going through the forward pass of the neural network. So there is no loss calculation and there is no back propagation. It's just going forward, and that's why the compute of it is much, much less than the compute of pre-training, for example. So important to note that working memory is going to be more reliable than models' vague recollection what's happened in the pre-training. So we have to use the context window to our advantage. So users should provide data for model to work with, given the context window allows. So if you could provide any information in the context window, whether it's documents, images, and text, then do so, because this is the working memory of the model. And it's better to rely on that than rely on what the model knows, which it was in the pre-training or post-training, which is, as we mentioned, it's statistical at the end of the day. And so let's define what the context window is basically the maximum amount of text token the model can consider at once when generating a response. And now this differs from one provider to another. So ChatGPT 5 has a context window. ChatGPT 4 had probably a less of a context window size. Gemini has a context window size too. So each provider provides a context window. So now the trend is to have bigger context window, and we need to take advantage of that. So we have to remember that the ChatGPT or LLMs don't have any persistent memory. Meaning once you finish that chat, you send your prompt and you get your response, the memory is not carried from that session to another unless it's done through the context window. So if we don't, so obviously ChatGPT actually is going to take the conversation and reinsert it into the context window. So this is why it feels that you feel that ChatGPT has persistent memory, is because of that. But in reality, there is no persistent memory. So once you finish processing something, the LLM will forget everything, but it is reminded using the context window, right? So context window is basically the driver each session. So it's good idea sometimes to reset the context window frequently, especially when you're changing topics, because you don't want the old material from the old topics affecting the actual prediction. And also it could be for information overload. Maybe you're overloading the system, you're using too much of the context window, so it's better sometimes to reset the context window. Now, of course, given how big the context windows on some of these models are, it's there's more flexibility into that. Sometimes you would want to keep some of these very related because it gives context to your question and so on. But it's a good idea every once in a while to clear that context window. It's very important since we said that context window is going to allow for working memory. It's a good idea to paste document, upload documents, use images, whatever you want to provide the model with, that would be a good idea to do so. So again, context window is going to vary depending on the the chatbot you're using. So larger to context windows is huge advantage for you because it allows you to provide more examples on your query. It allows you to upload documents, images. It's gonna allow you to have a better response. So let's zoom in a little bit more into the difference between the parameterized pre-training and the actual working memory. Actually, Andre Carpati, he basically gave a very nice wording to this. He referred to it as vague recollection, which is basically refers to what's happening in the pre-training, because he understands that the pre-training is actually statistical, which means not everything is going to be remembered. There's going to be a vague recollection of things. So it feels like a long-term memory, general fact, patterns, and association learned from vast amount of data, but not tied to any specific recent interactions. So things that it sees frequent, it's going to remember. Things that didn't see frequent, it will not remember. Now, while working memory is the memory in the context window, and it's going to be very important for inference. It includes the current dialogue, recent inputs, and any tool output. So if you search something online and you copy paste it into the prompt, so it's going to allow the model to reason, reference, and respond coherently. So there's a difference between the two. I mean, you don't want to rely too much on the vague recollection. You want to rely on the working memory. So it's important to remember that LLMs don't have any form of persistent existent. And this is again Andre's terminology. And so each time they start up, they process token, produce outputs, and then they sleep, they shut down, forgetting everything. It's through the context window that they're allowed to remember. So for example, ChatGPT, they include things in their, so they try to include your whole chat window, whatever in your chat window, into the context window, to basically to wake up the LLM so it remembers all that material. So once they are used, they rely entirely on the information provided within their context window to recall and reason. Now, AI companies, you use the context window also. They do something called load context, which is basically instruction that guide the model's behavior and respond, also known as system prompt. So they have system prompt of their own to make sure. So every time you're pushing the input into the neural network, you have that part also pushed with your actual query. Uh, and we're going to see an example of what's actually being pushed in the context window. So the context window is going to act like a short-term memory buffer, letting the LLM think with fresh, specific information instead of the vague general knowledge it absorbed during the pre-training. So here's an example. This is a visual example. So this is the context window here. So part of it is your latest inquiry, your latest token, the last thing you've written in the ChatGPT portal, and then there's the chat history from that chat also that is being pushed in the as part of the tokens, and maybe some predefined user tokens. So sometimes you're able to actually change the setting and make the chat GPT resemble more to what you want him, her, or want them to sound like, to feel like. Plus system prompts, these are things uh, prompted by ChatGPT, Gemini, and so on. So when you're actually writing a question on ChatGPT, it's not only your question that is being pushed into the neural network or into the LLM. It's actually more than that. It's your whole chat, maybe some things about your chat history, and then a system prompt from the company that is providing the LLM. And on top of it, sometimes a chatbot finds content from the net to help answer user queries and shove it into the context window. So also, the LLM might be using the internet and it goes searches something on internet and it pushes it also part of your of the context window. Now you could do that on your own, right? I mean, you could copy and paste things from the internet and put it as part of your prompt. That could happen too. But nowadays, I mean, with a lot of these LLMs, they have internet search built in. So they're actually also finding some stuff on the internet and pushing that part of the context window, especially when you're asking about information that is quite recent, because the pre-training in these LLM models happened a while ago. It could be a year ago, 6 months ago, or whatever the case is. So when your question is about recent phenomena, then it's gonna try to find things on the internet and push it as part of the context window. So by allowing the LLM to use tools and use the internet, we are taking advantage of working memory, and that's the whole point. So we turn a passive pre-trained model, limited by what it has learned in the past, into an active system that can retrieve, verify, and refine information dynamically. So the internet is a great tool that LLMs can use. It's going to enable real-time retrieval of current information or niche information. Sometimes, your question sometimes has to do with something so niche that probably the LLM has forgotten it's in pre-training. Because remember, it's going to remember things that are frequent in the data. Things that are not frequent, it's not going to remember. So for that niche, it's very helpful to use the internet. So it transforms LLM into a live researcher capable of verifying facts, checking sources, and staying current. Code execution, the allowing these chatbots to actually use Python, and that's going to be so powerful. For example, LLMs could now, because of this, could perform calculations, mathematical calculations accurately because of the use of Python. So even though they were trained on text, the fact that they could use a thing like Python will actually is a huge shortcut for them because they could just use it. It's like somebody using a calculator. Documents handling. It's the ability to upload documents such as PDF, Excel sheets, and so on is gonna maximize what you could get out of the working memory of an LLM. Again, you have to always remember that LLMs are going to remember better things they have seen often in the training. Things they haven't seen often in training is quite, they're not going to remember that well. So other tools it could use retrieval augmented generation RAG, which allows LLM to recall facts from custom or domain specific knowledge. So these are things like peer-reviewed scientific papers and so on. Now remember, I mentioned at the beginning that LLMs, ChatGPT has been trained on the public available data of the internet. So it's not the whole internet. And a lot of times what's available for the public on the internet is not the high quality data that you would need for an LLM would need to verify information. Now, so it's very important to have access to these databases, and this is what it takes us to the next tool, which is databases or API access to things like medical information, financial databases, and so on. These are verified private databases that now these LLMs have APIs to be able to access. And then the last tool, I believe this is the last tool. Obviously there's more tools, but I basically wanted to summarize the most important one. And the sixth one is planning, simulation, and agentic tools. So planning is, remember, LLMs are probably very poor at planning, so you need to give them some help with that. So agentic tools. So the LLM is able to move from passive response to active problem solving. With planning tools, the model can break complex goals into organized steps. So they would break the problem into smaller ones. Um, and then agentic tools will allow it to execute those steps without instructions, retrieving data, calling APIs, and adapting its action based on results. So let's go through this activity. Please pause the video to read it and think about it. So here we're dealing with a leading AI chatbot, and you're asking it about your favorite sporting event that just finished a week ago, last week. But the chatbot gives you answers about the preceding tournament from 4 years ago. So this tournament happens every 4 years, and you're asking it something that happened a week ago, but it goes back to 4 years before. But you try another chatbot, not that more powerful than the first, and it nails it. It gets the answer correctly. So what's going on? So probably the second LLM has access to the internet. Having access to the tool of the internet, so it could retrieve the latest world information, including sport events that happened just a few weeks ago. So using the internet is a clever way to get LLM to be more useful. So now that we have talked about inferential, now let's talk about what the user can do in terms of the prompt itself. Forget about what they attach in terms of information, the documents they attach. They ask the LLM to use the internet or to use a specific website or specific text. So what else could a user do? Well, there's some sampling techniques which are actually some people consider it as part of prompt engineering, some don't. So let's think about prompt engineering is basically we are trying to design prompts that guide the model to produce better results. So results that are more relevant, accurate, or creative. So you're playing with the prompt to get a better result from the model. Uh, so remember, LLMs predict the probability of each possible token, and it assigns likelihood. So deep learning is very powerful, is 43%, so it's going to pick powerful. But does it have to pick powerful? Maybe it could pick innovative. And so before we talk about go deep into prompt engineering, let's talk about examine sampling techniques. And these sampling techniques will have to do with which word do I pick? Do I always pick powerful, or maybe sometimes I pick innovative? Maybe I pick complex, and so on. So with the sampling techniques, we start with the temperature. So temperature is basically going to control the randomness. As a matter of fact, I think it's still available. There is the AI studio for Google Gemini. It actually allows you to change the temperature and to actually see the difference it makes. So the degree, so it's basically temperature is the degree of randomness in token selection. Lower temperature produce more deterministic response, less random, while higher temperature are going to be more diverse. So higher temperatures are going to give you more randomness, more creativity. And so while lower temperature is going to be uh, very, very deterministic. So things that are not creative, so things that are much more factual. So depending on what you want from the LLM, if you want the LLM to write a poem for you, then you would probably use a higher temperature. If you want the model to be very factual, then so for example, if you wanna collect some facts about a certain event, then probably you're gonna use a low temperature. And again, why are we able to do this? Because these models are statistical, and anybody taking statistics understands this very well. In statistics, I mean, you could make the model a little bit more deterministic, less more probabilistic, depending on how you deal with all these parameters that you're dealing with. And you could be more confident about certain things given what we in statistics we call confidence interval. So this is a somewhat similar idea where if we want to we control the temperature to make sure whether we want to be very confident about our answer or less confident and more playful. There's also other tools, not only temperature. We have the top K, which basically if you set K equal to 50, so it's gonna consider all 50. So out of the probability distribution, it's gonna consider 50 tokens, and from that it would pick the choice. While lower K makes it less creative. So for example, if K is equal 1, that means it will always take the top probability, the word with the highest probability, always with K equal 1. So K equal 1 forces the model to always use the highest probability token, while higher K numbers will allow more words to be part of the sampling. The top P is basically it's basically takes the cumulative probability, and we're going to show an example of this. So we're going to show an example what I mean by cumulative probability. But I mean, we're looking at 4 probability that add up to something, or the 6 probability that add up to some number. And length is also important. Sometimes you want to control the length of the response that the LLM gives. You don't want a long response. But remember, shortening the output length doesn't make the model more concise. It simply prevents it from further elaboration. However, this approach offers several benefits. So there are benefits such as saving energy, having concise results for the user. So maybe you don't want to go through all the details and the elaboration. You want the first few lines. I find this very useful sometimes. I don't want, I don't want my LLM to turn into a Google search, where you have a whole page answering. I want the top most important things for me to remember. So let's pause the video and look at this activity. Let's go through this activity step by step. So the idea is we're taking the cat sat on as an input, and we're asking the question, and this is the probability distribution. So here we say on mat, floor, chair, table, roof. And the first question is, how would the result differ if the temperature is set to 1.7 and 1.5? So let's start with A. So what happens if we change the temperature? So this is here is if we set the temperature to 1, so we end up with the same probability distribution, nothing changes, right? So it's going to stay the same probability distribution. So we're more likely to choose mat, but there's a possibility that we choose floor, but it's most probably is going to use mat. Now, when we decrease the temperature to 0.7, then we give the mat even a higher probability. So mat becomes 0.6 instead of 0.5. So we give mat a higher probability now. And the curve narrows, so you're more likely to choose uh, tokens that actually are of higher probability. So it becomes a little bit more deterministic. While if you choose a temperature of 1.5, the distribution curve is going to flatten and we end up with matte having a less probability and floor and so on. So instead of 0.5, now we have a probability of 0.4. So now you're more likely to choose something else other than temperature. So note, changing the temperature only changes the distribution, changing the probabilities around, right? While the K, we will see the K is a little bit different. So the top K is basically we are restricting the model to choose the top word. So if we say K is equal 1, then definitely we are forcing it to choose matte. If we use K equal 3, then we're forcing it to choose between matte, floor, and chair, while still taking into account the probability distribution. But here we're eliminating all the lower probability words. Now remember, this is just an example. I mean, in a real case scenario, probably you're gonna have dozens, hundreds of probability of words that come, tokens or words that are gonna come in terms of probability. So now let's take top P. So top P is we're looking at the cumulative. So we add mat plus floor plus chair, and we end up to 0.95. So we meet the threshold of 95. So we only consider these numbers that are so include the smallest top token where cumulative probability is less than 0.95. So we only consider this. While so then if we renormalize these four, so the four that we picked, table, chair, floor, mat, so now we renormalize them based that, so we reintroduce them now, except for the fact their probabilities are going to add up to 1 now. So so the first mat is going to go increase to 0.5 to 6. So 0.8, on the other hand, we count the cumulative, so we end up with 3. And again, we normalize them. Again, it's the same, same idea. Again, we're trying to restrict or change how the LLM is gonna pick the actual words based, changing the distribution around. So engineering by the basic prompting technique, which we start with, is the zero shot prompt. So zero shot prompt is basically you're just asking the LLM to do something without giving it any examples. So do this for me, summarize this text for me, respond to this letter for me. Just one shot prompt, very simple. Now, so no examples are provided in this. A multiple shot prompt is when you start writing examples, telling the LLM to use some form of framework. So for example, you tell it summarize this text into and give it an example of a summarized text that you've done. Or another better example is you want it to write a letter with a certain tone, and then you give it an example of that tone that you want, and so on. Contextual prompting provides specific details on the background information relevant to the current conversation. So you're giving the prompt some context. It's not just summarize this text for me. You would say, well, this is text that has to do with the medical diagnosis and so on. So you give it more context about the summarization that needs to happen. So you need to give some detail on the background. System prompting is you set the overall context and purpose for the language model. So here we give the purpose, you give it the big picture, and this is usually set by developer. While so basically it's things like you tell So the developer might want the LLM to act and behave like an expert math tutor and explain concept step by step. So we see this a lot in um, second tier companies that work with LLMs. They might want to um, modify the LLM or improve the LLM so it can answer specifically to a certain tasks. So, for example, if let's say some company is in the post-secondary education industry, and it takes the LLM and it will basically try to develop it so it helps students in a specific math course or a specific physics course, and so it will have to do some form of system prompting in the background to make sure that the LLM behaves in the way it wants it to behave. Role prompting is something the user could use. So you could ask the LLM to be a sarcastic movie critic, to be a supply chain professional. So answer the question as a supply chain professional. Answer the question or the prompt as a psychologist. So here, this is set by the user, more widely set by the user. So now we move on to two other advanced prompting techniques. The first advanced technique is the step back. And here you give basically the LLM a general question first, then apply it to a specific task. So you ask it to a general question related to that specific task at hand, and then feed that answer that you got from that general question into the prompt. So for example, instead of directly asking edit my text, first ask what makes a good text editing procedure. So you're asking the LLM to give you the guidelines for a good editor, what a good editor would do, and then use that answer as part of your prompt. Self-consistency is sampling multiple outputs using high temperature, and the idea here is to have more than one path. So to allow LLM to generate multiple reasoning paths and picking the most consistent answer, rather than just relying on one single most likely next word. So this is done at high temperature to ensure diversity. So for an example is what is the best way to motivate a team for a team project? The model generate three reasoning paths, set a clear goals and recognize achievement, give team members autonomy and celebrate milestones, set goals and promote objectives. And then you could I don't know, sometimes the LLM itself would basically pick the best one out of these three, or you could be the one that decides, well, I see the word set clear goals as redundant in all three, so that must be something good. So something good to have. Chain of thought, the idea here is to generate intermediate reasoning steps. So assist the LLM by having it generate intermediate steps before giving the final answer. So it's basically so the idea is instead of asking who will win a chess match between player A and B, directly prompt the model to reason step by step. Consider players A opening strategy, mid-game tactics, and end-game skill. Then consider player B's strengths and weaknesses. Based on that reasoning, who is more likely to win? So, for example, if I'm looking in, let's say in football, Brazil is playing Germany. So instead of just asking it who will win that game, well, you would go intermediate steps saying, well, Germany's strengths are the following. What are Germany's strengths and what are Brazil's strengths and how are they ranking nowadays and so on. And then basically you're prompting the LLM to use chain of thought. So intermediate reasoning step. Prompting by code, on the other hand, is just basically asking the LLM to use code. And I use this often, just get the LLM to use Python to do something, especially when it comes to calculating something. It's better. You're always at a better place when you ask it to use Python. One example here, instead of asking it how many R's are in strawberry, which usually LLMs usually get wrong. Ask to use Python to count the numbers of our in Strawberry. Right. Then we move on to tree of thoughts, which is it's going to have a multiple reasoning paths, and each path will use COT, chain of thought. So it's going to combine both the COT and self-consistency. Instead of following a single reasoning path, the LLM is going to explore multiple reasoning paths together, building a tree of possible solution. This increases the chance of finding more accurate uh, and creative answers. So TOT is usually requires special instruction or code that's not typically used in a normal chat box. React is something probably all of you have used already, which is basically to let LLM tackle complex tasks by combining natural language reasoning with the ability to take action using external tools like search engine calculators or Python code interpreters. So, for example, when you ask LLM to find the current weather in Tokyo and suggest what to pack for a trip there, you might want to ask the LLM to also use the internet. So in step one, the model decides it needs the latest weather data, which by using the internet, it could get that. It could search the weather in Tokyo, and based on the temperature and forecast, it could recommend something for you to wear or to pack. Um, So for example, so for temperature, let's go back to temperature. Sometimes, for example, chatbots don't have the ability to increase or decrease uh, temperature. So for example, ChatGPT, there is no toggle or button for you to adjust temperature. So what you would do in that case is you would include it in the prompt. Say things like answer concisely and factually. That will basically prompt the LLM to use low temperature. Give a straightforward explanation. List the key facts only. List the key facts only is also going to push the LLM to be more deterministic and less random. Or you want it to simulate high temperature, you use words like be imaginative. Write in a creative way, give a creative interpretation or analogy, and so on. So at the practical notes, so before we move on to the activities that I have set up, so practical notes um, for math, if you have math problems, then ask the LLM to use code interpreter or for calculations. Planning, use step back or tree of thoughts to explore options. Uh, Output length, if you want something to be more concise, then you could ask the LLM to constrain its output length. If you want more reasoning, you might want to use chain of thought to guide step-by-step thinking combined with self-consistency for accuracy. Now, remember, a lot of these models now, they have the option to use a reasoning model within the LLM, and that in itself uses some form of chain of thought. If you wanted to use up-to-date information, then ask the LLM to use the internet. Um, Text tasks ask for editing guidelines first, then apply. Remember, if I'm going to ask it to edit something, then I'm going to ask something like, what would a professional editor do? And then take whatever LLM comes up with and use that as part of your prompt. We see this a lot also in image generation. So, for example, if you have an idea of an image to generate, you give it to LLM and you ask LLM to draft for you a prompt that will basically encompass what you want done visually, and then you would use that prompt to prompt for an image. So this activity, again, always pause the video if you want to read the activity and try it on your own before you see the answer. So there's a user prompt and LLM as follows. A farmer has 17 sheep and all but 9 run away. How many sheep are left? The LLM gives an incorrect answer of 8. because it thinks 17 minus 9. Um, so the LLM subtracts 9 from 17, which is not the right thing to, it has to remember, it has to understand that all but 9 run away, so actually 9 remain. So how could we fix this using a chain of thought? So we would prompt it saying, let's solve this step by step. A farmer has 17 sheep and all but 9 run away. First, interpret what all but 9 run away mean, then determine how many sheep remain. Finally, give the answer clearly. So the idea here is when you find a question, especially word problems, try to break it down for the LLM step by step. Again, a lot of times these LLMs are really powerful. They could get things like this. So start with a one shot, maybe, sorry, zero shot without example. See if it solves it. If not, then maybe try uh, the COT prompt. So if you do that, then the LLM is going to give you the right response and the final answer, which is 9. Again, you could pause this video to read this activity. So this prompt, for example, which technique? So I'm asking you that I'm going to give you this prompt and you tell me based on this prompt which technique I'm using. Generate 3 different reasoning paths to summarize the following paragraph into a sentence. Then choose the summary that best capture the main idea across all reasoning paths. So this is obviously self-consistency. So here another activity, again, pause the video. So you are planning a team building event for 20 people. The goal is to improve collaboration and morale. The budget is $1,000. Suggest the best activity. So you prompt the LLM and get a suggestion to go for a group dinner and no information about the pros and cons. So once you just use this as a prompt, so basically a team building event for 20 people and the goal and the budget, you prompt the LLM and get a suggestion to go for a group dinner. So it suggests that you go for a group dinner with no information about pros and cons. So in this case, what would you do? You would want to use TOT to improve the LLM response. So let's explore multiple reasoning paths before deciding. Goal, so you set the goal, plan a team building event of 20 people, budget 1,000, and improve collaboration and morale. So that was your goal. That was your initial prompt, which didn't give you a good answer, but now you instruct the LLM to do steps. So generate at least 3 different ideas and activities. For each activity, it's going to think of the pros and the cons, compare the options and choose the best one based on the goal and constraint. And finally, provide recommendation. So it's gonna generate 3 different ideas and then finally choose between these 3 ideas. Here it chooses the escape room and snacks. And here, this is good for 2 reasons. First of all, you're understanding that it went through different ideas. So you know it's chain of thinking. And also you end up knowing why the final choice was made. So this is a huge advantage using TOT for this. Now, for this activity, again, pause the video if you like. So you're writing an email to a client to reschedule a meeting because you have a conflict. The tone should be polite and professional, your prompt. So you want to write an email and the tone should be polite and professional. So you prompt the LLM as follow. Write an email to reschedule a meeting. The LLM writes, "Hi, I need to reschedule our meeting. Let me know what works for you." Then obviously this is too short, lacks context, and might sound abrupt. So we want to use COT to improve the results, chain of command. So you would basically prompt the LLM to think step by step, identify the key details, decide on the tone, include an analogy for the inconvenience, suggest an alternative date, and end with appreciation and openness. So you're basically not just giving a zero shot prompt. you're basically steering it into thinking and the right way. Obviously, the answer that you're gonna get is gonna resemble more what you really want. Again, if you want to read the whole thing, you could pause the video and read it, and you can always download the whole PowerPoint also. And this is an example, activity 16 of the use of the internet. So basically triggering the LLM to use the internet. So if you ask, find the current temperature in Montreal and calculate the average temperature for the past 7 days. Now, are you guaranteed that the LLM uses recent data? Well, I mean, with the new LLMs, maybe sometimes with these LLMs that automatically decide if it want to use the internet or not without asking you to prompt it. But I mean, why not prompt the LLM to do that? I mean, that's even safer because you don't know if it's automatically doing it or not, or relying on some historic data. So the idea is just let the LLM to rely on new data. So maybe you might ask it to go on the internet and use new data and maybe give today's date and and so on. It is going to give you the results. Now note that some LLMs might be automatically doing this without instruction, but still it's a hit and miss. So instructing the LLM guarantees more accurate response. So this is done automatically by the current latest versions of LLMs, but you might want to do it to make sure you get the right response. So now the models that we have currently, we have the base models, the standard, sorry, that's not the base model, the standard models, which is basically the pre-train, post-train, what we've seen. We have the thinking models, which is pre-train and post-train. And while part of the post-training is actually there is reinforcement learning. So these are called thinking models, and you find them everywhere. And now I think ChatGPT with their newest model, they basically lumped everything together and they automatically decide which model to use. But there is other, whether it's Gemini or the DeepSeek and on, they still give you that choice. So you would want to use thinking models, especially for mathematical problems or things that questions that involve analytical skills. Deep research models are basically a combination of thinking model and tool usage. So you're doing both. You're asking it to, so it's thinking and it's using tools. And it might be using incorporating chain of thought in the background. And there is also obviously the multimodal LLMs that can process images, audios, and videos alongside texts. So you see all form of these models out there nowadays. Uh, so let's do this activity, and I'll give you a few seconds to read. So you imagine you're tasked with building an AI. So you're the guy or you're part of the team that builds the AI. And you want it to be able to answer complex questions. So you have four possible steps. So first of all, you feed it the entire internet available to the public, so it learns the language patterns and predicts the next token. Second step, you show it some example of good questions answer pairs. And third step is you let it practice thinking, reward good reasoning and discourage bad ones. And fourth is you give it internet access to look up facts and when it gets stuck. So if you stop at after step one, what kind of AI do you have? Well, if you just feed it the whole internet without any post training, then you end up with a base model. I mean, that's what we talked about at the beginning. If you stopped at step two, then you're doing post training, right? But only supervised fine tuning. If you stop at step three, then you've done some reinforcement learning. So the model is going to be probably will do better on these analytical questions and math-based questions. Step four is when you allow it to do deep research, right? So yeah, it has tool usage and it has thinking, deep thinking. So combines long thinking chain of thought with external search, allowing deeper, up-to-date reasoning. So base model. So at the end, we're nearing the end of the presentation, the end of the crash course. So base model, only few viable companies would like to do their own post-training and they would be interested in the base model. So these are companies that they want to do their own post-training based on their own probably reinforcement learning and so on. Um, um, Now, the open weight models are basically models where the weights are available for public. And an example for this is Llama 2, Falcon, Mistral, DeepSeek, Quan from coming from China. All these are open source, open weight model. And these you could, if you like, you could actually fine tune them to your specific task. The closed weight models is what we've seen, that's basically the GPT, the Gemini, the Grok, all of them are closed weight models. Here is going to charge you money for API usage. And so you always need these APIs. So you have three cases, the base model, the open weight, the closed weight. I mean, the main choice is going to be between the open model and the closed weight model. So the cost for the one thing with the closed weight model is the cost tends to be high, especially for API fees, but customization might be low. While it's high, the open weight model requires a lot of customization, but if the customization takes place, then the cost is only the infrastructure, the compute, right? Um, Now we move on to one of the last topics, which is latency and performance. And latency has to do with how long it takes for the model to respond after you send the prompt. And the time includes is basically your prompt, the time it takes you to write the question, the time it takes for the model to compute the next token, time before you see the first word, and then how fast the rest of the text appear, which is generation speed. So bigger models are going to basically take more time to compute each token, but probably bigger models are acquiring bigger GPUs, which means they're doing this faster. There's network delays, also internet and server. You're prompting ChatGPT, there is also server issues. Long prompts, if your questions are long, it's going to take longer. If your questions are shorter, low temperature, general settings. So also, if you want more creativity opposed to less creativity, also that gonna impact the time. Um, Caching frequently, here you're basically reducing latency because the context window is going to be smaller. Also, context window is going to play a role into this. Now, when it comes to latency, we have data limitation. Not for competency. Now we're talking into data and compute in LLMs. So basically, with latency, uh, you have some options. Probably you want to use shorter prompts. You would want to cache often. If a question doesn't need to be complicated, then make it simple. There's no need to complicate things when they don't need to be complicated. Now we're going to talk about the data and compute, which is the challenge in these LLM models. So we have the data limitation. So we only have enough material that is available to public on the internet. So there's only so much there is available to the public in the internet. So what are companies are doing to to fix this or mitigate this issue is basically they're trying to get AI to generate training data, expanding into multimodal. Yes, we've used all the text on the internet, but there's plenty of other sensory data such as videos and audio that could be used. And remember, high quality opposed to low quality. Low quality data is like calories without nutrients. So just because you have a lot of low quality data is not as good as having less of that data but of high quality. Compute limitation. Now we also so even if you have all the data that you need, then there's going to be the compute limitation, which is chip availability. So, for example, Chinese companies might not be able to access some of the chips that are produced in the US, the state-of-the-art chips. And there's issues with capability and cost. So maybe the chips are available, but you don't have the capital to buy these chips. And there's also the energy requirements. So running these chips require energy, requires cooling, requires big data centers. And data centers are basically where the compute is hosted. It's not just about housing chips. They are optimized for power efficiency, advanced cooling, dense GPU clustering. So the constraint here is not just that they are in the chips, but also in the energy and the thermal management that are required to run these LLM models. Now we need to move a little bit back into to latency, and we have something called test time compute, which is also referred to as inference time compute. And basically, it's the amount of computational work and a trained LLM model does when it's being used. So it's basically includes core and supplementary compute. So we thought we touched a little bit on it when we talked about latency, but now we let's clarify it. It's basically two different computes. There is the core compute, which is basically, remember we said that once you input the prompt, that prompt has to go through the neural network, through the forward pass of the neural network. Um, and it's the context window that decides how big the input is going to be and how much you use of the context window. And the context window in most cases will include the system prompt, the chat history, and user instructions, if any. And that's the core compute. Now, the supplementary compute is maybe you're using some sampling strategy. Maybe you're saying things like be creative or be strict or be factual. A chain of thought also might require some form of compute. Tool usage is also going to be involved in compute. So in conclusion, we have to remember always, and I think if there's one thing to take from this crash course is that LLMs are based on statistical models, meaning we should expect uncertainty. Not all the outputs are going to be factual. Document handling. We have an advantage nowadays that we could attach documents, and that would narrow down some of the thinking or the information acquisition for the LLM. If we could provide PDFs or Excel sheets or whatever the case, that's going to help in getting the result we want. Take advantage of working memory. So take advantage of the context window. Allow LLM to use tools. Give a lot of detail and information about what you're asking about. To combat hallucination, using the prompt, provide document to ground the LLM, prompt the LLM to allow for critique and factuality. So allow it to tell it to be critical. So one thing I do always with my prompts is I start with the word be critical. And this actually helps me on the last point, which is LLMs are sometimes designed to be psychopathic, which basically they're gonna try to pamper you and tell you what you want to hear. And to basically mitigate that, you just want to tell it to be neutral in the prompt, tell it to be critical, and that will help you get results that are not just trying to pamper you, but they're honest and truthful. So thank you very much for watching, listening, and remember you could download the whole PowerPoint presentation that would help you to navigate this video. Thank you very much and have yourself a wonderful day.